Have you ever stopped to think about how we feed, well, everyone? A planet of 8 billion people? The answer, and this might surprise you, isn't just in the dirt. It's actually in the air. And it's all thanks to this incredible balancing act, what we're calling the Great Chemical Compromise.
Okay, get ready for this because it's a wild one. About half of the nitrogen atoms in your body came from a factory. No, seriously. The food that keeps billions of us alive is possible only because we figured out how to pull a crucial ingredient, literally, from thin air. It sounds like magic, but nope, it's just some really, really clever chemistry.
So the big question is, how on earth do you turn air into, well, the building blocks of life? Let's dive into the chemistry behind it all.
All right, let's meet the star of the show, ammonia. You're looking at it right here, NH3. This little molecule is the absolute backbone of the nitrogen fertilizers that have let us feed a planet that just keeps growing. I mean, to put it bluntly, without this stuff, our world would be a way hungrier place.
And what's so amazing is where the ingredients come from. I mean, they're everywhere. Nitrogen, it makes up 78% of the air you're breathing right now. And hydrogen, we just pull that from natural gas. So, the raw materials are super common, super cheap. The real challenge, the trick, is getting these two to actually combine.
And that's where this game-changing invention comes in. An invention that literally changed human history. It's a process that basically works like a giant ammonia machine.
Okay, so this is it. This is the Haber process. Let's follow along, right? You've got your nitrogen and hydrogen going in. First, they get squeezed under insane pressure in that compressor. Then they're heated up to crazy high temperatures. They flow over this iron catalyst. That's the magic ingredient, which forces them to finally react and become ammonia. Then, as everything cools down, the ammonia turns into a liquid and gets drained off. And the best part? Any leftover gas just gets recycled right back to the start. It's this beautiful, super efficient loop.
But, and this is where the story gets really interesting, making this machine work well isn't as simple as just, following a recipe. It's all about finding this perfect, but also kind of imperfect, sweet spot of conditions.
And that right there, that's the heart of our whole explainer. It's this brilliant trade-off, this balancing act that we're calling a chemist's compromise.
So, what is that perfect recipe then? I mean, think about it. If you were in charge, what temperature and pressure would you pick? Well, turns out it's not so simple.
This table pretty much sums up the whole problem. You want a high yield, right? Meaning you want to get as much ammonia as possible. For that, you need low temperatures. But you also want a high rate. You want it to happen fast. And for that, you need high temperatures. See the problem? You literally can't have both. The perfect setup for one is the absolute worst for the other.
And this graph just drives the point home. Look at that red line way down at 350 degrees Celsius. The yield is amazing. But as you crank up the heat, see the purple and blue lines? Your yield just tanks. But here's the catch, the big but. At that nice low 350 degrees, the reaction is so slow. It's like watching paint dry. You'd literally go broke waiting for the ammonia to show up.
So this is it. This is the big compromise. The chemists decided on 450 degrees Celsius. Yeah, it's not the best for yield, you lose some product, but it makes the reaction go fast enough to actually be practical to run a business. It's that perfect sweet spot between how much you get and how fast you get it.
And it's the exact same logic for pressure. Sure, higher pressure is way better for the yield, but think about it. Building a factory that can handle that kind of pressure? It's incredibly expensive, not to mention dangerous. So, what do? They settled on 200 atmospheres. Again, it's that sweet spot, but this time it's balancing efficiency, cost, and safety.
So what's the secret sauce that makes this whole compromise possible? It's the catalyst. In this case, it's iron. Now, the iron doesn't magically increase how much ammonia you can get. What it does do is make the reaction happen way, way faster. It lets you get to that compromise point so much quicker, which is what makes the whole thing profitable. Now, this whole idea of making a compromise, it's not just a one-off for ammonia. It's like a core principle for all of industrial chemistry. So let's take a look at another super important chemical, sulfuric acid. Sulfuric acid is kind of the unsung hero of our modern world. Seriously, you can pretty much judge how industrialized a country is by how much sulfuric acid it makes. It's in everything: car batteries, fertilizers, detergents, soaps, you name it. And the process to make it, called the contact process, uses the exact same kind of compromise logic.
Okay, so check this out. When you put the two processes side by side, something really cool pops out. The temperature? Exactly the same, 450 degrees Celsius.
And for the same reason, it's that balance between yield and speed. But look at the pressure. It's totally different. How in the world does the contact process get away with using just 2 atmospheres? That's barely more than the air pressure around us right now.
Well, the answer is just in the chemistry itself. The reaction to make the key ingredient for sulfuric acid is just naturally super efficient. We're talking a 96% yield even at low pressure. So there's just no point in spending all that money on expensive, high-pressure gear. It's the same thought process, the same compromise logic, but because the reaction is different, you end up with a totally different and way cheaper solution.
So what's the big idea here? What does this all mean? It means the very foundations of our modern world are built on these kinds of smart, careful chemical compromises.
And that's really the main point we want you to take away. These industrial processes, they're not just lines in a chemistry textbook. They are incredible feats of engineering. They're this delicate 4-way balance between speed, how much you make, how much it costs, and, of course, making sure the whole thing is safe. This kind of thinking is what gave us the ability to feed billions of people and build the world we live in. Which really makes you wonder, right? With all the new challenges we're facing today, with energy, with new materials, with sustainability, what's going to be the next great chemical compromise that changes our world?